So I came across this idea or this paper about prompt tuning, and I thought it pretty cool. So I um, implemented it, played with it, and I wanted to share what I've learned. Um, the prompt tuning is similar to model fine tuning in its purpose. The purpose is to take an existing model and make it tune into what you want. But the way it's really different from it is in model fine tuning, you are changing the parameters of your model. In prompt tuning, you're still training something and tuning some parameters, which I will talk about, but the model itself and all these parameters remain frozen, unchanged. And that has a lot of advantages that I will get into. But let me show you the net results first. So if I can zoom in here, hold on. Okay. So the horizontal axis is the number of model parameters. Vertical axis is the performance of the model. The blue is the model as it comes. The green is this idea that I'm going to talk about, which is you take the model in blue and you do prompt tuning on it. And then the orange and red are model fine tuning. And what this one is showing you is with prompt tuning, you can get a lot of boost from the base model. And I will show you it comes at really small compute cost. And as a matter of fact, if the number of parameters is large enough, the performance of the model tuning and prompt tuning converge, which is really powerful. All right. So that's one idea. The other idea is here. If you look at the left, the world of model fine-tuning, let's say you have 3 different tasks. You take that pre-trained model, that blue model, and you essentially fine-tune 3 models out of that, 1 per task. And if your model has 11 billion parameters, you're gonna end up with three of that, 33 billion model parameters laying around. Now let's look at the prompt tuning. So in prompt tuning, you use the same model. Model parameters are frozen. So you still have those 11 billion parameters and no more of that. And what you do here is you create a bunch of custom tokens, new tokens for each task. So say task A, I'm going to create 10 custom tokens. Task B, same thing. Task C, same thing. And when you send your prompt to this pre-trained model, you prepend your prompt with your task-specific custom tokens. And what that means, what you have to do now is to have a way of creating meaningful embeddings of the newly created tokens. So prompt tuning is essentially fine-tuning of a very small matrix for the embeddings of custom tokens, such that when you prepend them to your actual prompt, it does make the model behave in the way that you want. All right. So that is that idea. Let me show you another illustration that I liked a lot in this GitHub thing. So at the lower right, you have your text input, that's your prompt. You send it into text embedding table. And also what is not included here is your position embedding, but that one goes in as well. And after these steps, you end up in this text embedding, which is an array of embedding vectors. And the length of it corresponds to the number of tokens in your input text. And this is where prompt embeddings or prompt tuning comes into the picture. If you remember, I mentioned you're going to prepend your text input with a few custom custom tokens, and you have your own embedding table for those custom tokens. So say you have 10 custom tokens, you feed it into that embedding layer or embedding table, if you like. That gives you an array of 10 embedding vectors. And now what you do is to concatenate the one on the left with the one on the right. So you're going to have your text input embedded as you would. And now, let's say it was 100 tokens, but now you have 10 that prepend to it. So you're going to have 110. And what your attention blocks are going to see, like essentially the rest of your model, is going to be that 110 embedding vectors. They don't know that 10 of them came from your newly crafted custom tokens and the other come from your text input, and that doesn't matter. So this is the picture we're going to work with. Let me show you the code. Maybe before I show you the code, let me explain what I'm trying to accomplish here, what I'm trying to prompt tune for. So then the under the hood will make more sense. So basically, I'm going to get this GPT-2 model from transformers. And then, without any training yet, I'm going to show you. Okay. Now, what I want to do with this is to look at the movie review and return only positive or negative. That's the whole purpose of this model. If I take my review, which is here, so this is a model that hasn't been trained yet, and I say the movie was absolutely fantastic, and now sentiment. These are the tokens it predicts currently. So the highest probability is for the colon token, and that's 366. The next one is a very, and the next one is actually kind of tricky to tell what it is, but it's the like next line token, \n. So this is what's currently producing. What we want to do is to prompt tune it so that it will either give you positive or negative. And let me show you the same model after prompt tuning of what it does. If I go here, I give it the same thing. Hopefully all of this is familiar now, but then you can see positive came out as 73 percentile probability. And interestingly, number 2 in that probability ranking is going to be negative and then lowercase positive. So it works. But let's see how we made it work. What I did here was, well, you have this GPT-2 model. Actually, there is a little class in the model.py that I will show you, but that's where it comes from. I'm getting my data set from datasets library, and that's IMDb, just reviews, and there is a label for each review, 0 or 1, negative or positive. All right, and let me talk about the data processing a little bit first. Let's see. So I'm defining my trained data set from that IMDb data set, and what I'm mapping here to each element in that is this prepare data thing. So let me show you what prepare data is. The prepare data is, well, it essentially creates that prompt that says, this is the review, and then you plug in the actual text of the review from that data set, and then you add sentiment. Now this is what the model will see. And we're also creating these labels, which is positive, yeah, if a label is 1, else negative. What's really important here is the way I crafted this label. Is space uppercase positive. And the reason I have it like this is because this maps to a single token. Here. So if I go to GPT-2 tokenizer and I put space positive, you can see it maps to a single one. Let me see if I remove that space. Now you have 2 tokens. And it just makes a lot more sense if I needed to invoke my model once, get 1 token, be done with it, as opposed to multiple things. All right, so that's that. And I am doing the encodings here and label IDs. Okay, so now let me explain what's going on here. Well, so you have this text, you want to tokenize it, which you do. Key idea here that threw me some errors until I figured it out is the maximum length is no longer the context window size, but context window minus the number of tokens that you're going to prepend your prompt with. And that's there. I'm also tokenizing this labels, which is positive, negative. And let's see. So I want to print. I printed one data point, or one batch rather, from this data to bring some nuances to your attention. Let's look at it. So the input IDs, this is essentially that tokenized text. But as you can see here, there is a lot of the same token, until at some point it stops and you get actual real tokens. So what's happening here is that because I have a batch that I want to feed into my training, all the input arrays should have the same length. So what I do is that I'm looking at the number of inputs in one batch, find which the maximum length or the input with the largest sequence of tokens, and then I'm padding all the others to match the same length. And for padding, I just picked a random token, which is end of text token. But you will see it doesn't actually matter what this value is. And the reason that doesn't matter is another thing inside of this batch is the attention mask. And the attention mask is telling us here, for all those padded tokens, assign an attention of 0, meaning just ignore them. Even though they're there, I don't want the representation of my embedding vectors, what comes here, to be impacted by those. So that's why I said it doesn't matter what the padding actually entails, as long as you have some padding so you don't get error. My batches have 2 data points in them, or 2 examples. And as you might have guessed, one of them doesn't have any padding because one of them is the one with the larger sequence length and the other one does. So in the training data, you have your input text with their padding. You have the attention mask to ignore what comes in the padding. And you also have labels. And this might be something relatively new here. So let me explain that. When you train the model or fine-tune the model, you want to put all the attention on making the right prediction on the last token, because that's really the only thing you care about. If you don't take any actions, the model will get tuned to make the best prediction of the next character, next token for all the tokens in that sequence, which takes away attention from what you really care about. Now, by convention, -100 in transformers means no. Well, it means that this doesn't associate with the loss. So the loss is going to be only associated with the label that is not -100, and sure enough, it's the last. It's the last one. The last one, this 36,138. Let's see what that actually is. So if I say, what was it? 36,183.3. Here, that was negative, right? So whether positive or negative, you include the token for that as the last element of your labels. So that was for the first example in the batch, and then for the second example in the batch, it's also negative. So there is a key idea here, which I kind of wasn't even familiar with. I always thought when you train these GPT models, you're constantly making predictions for the next token in the series, and your loss automatically accounts for the difference between your prediction and the actual next token. But that turns out to be not necessarily true. As a matter of fact, these transformers give you the flexibility to decide what labels you want to use for calculating the loss. And what we're doing here is we're taking advantage of that and assigning the label that we want, and everything else would be zero. Again, a more naive approach here would have been to go back to this input where I said sentiment, and then that was the end of it. Let me see if I can find it. One moment. Where is the... Here. You see, a naive way would have been to put a space here and just say positive, and then let the GPT train on predicting the next character. That wouldn't be efficient. So what I'm going to do is to leave it like this, and then assign the labels as a separate array. All right. So at this point, we're familiar with the data. I haven't shown you how to prepend or how to create those custom tokens yet. But since we just looked at the data, let's look at the training as well. Okay, and that's gonna be, and I will come back to creating the model with custom tokens. But what I want to show here is, so during the training process, there is really nothing novel here except when you go to, so the model is making a forward path, making prediction, and here I have a star batch, which means labels, input IDs, and the attention mask. You provide all the three. Alternatively, like if you want to go the naive way, would be to just give it an array of text or an array of arrays of text. But here we're not doing it. We're just feeding it input IDs, attention mask, and labels. And you calculate the loss. I wonder if I have the documentation up to show you that in fact, when you calculate the loss here, it accounts for the labels that you provided in this batch and compares the labels to the predictions. Then take a backward step. I'm accumulating the gradients because my batch size is 2. I couldn't afford a larger batch size because of my GPU memory constraint, but that's okay. We're accumulating gradients over 5 batches so that you'll end up with an effective batch size of 10. All right, and let me now show you the model. I want to go back here, show you how the model is created. This. So we're creating an instance of this, and this has a parent class which is up here, and this is essentially your GPT-2 model, except that you give it the number of custom tokens that you want to prepend your prompt with. In my case, I gave it 10, but let's see what it does. It will initialize the soft prompt, which are these custom tokens. All right, so let's look at how that works. Now, okay, let's see. So what it does is that you can either start a embedding matrix with random values, or just copy some of the embedding values from your token embedding, which turns out to be a good idea. So it does that, get the weights, and by the way here, look, the soft prompt, which is that embedding for your custom tokens, that's essentially an instance of the embeddings layer with a number of tokens. And then what it says here is that the embedding size should be the same as your GPT-2 embedding size. And then it dumps the model, the parameter weights from either random values or from your token embedding. All right, so that is how it instantiates it. But let me also show you this part. Hold on. Okay, right here. So remember I was telling you, you go for the prompt that you have, tokenize it, add it to the positioning embedding, and now you have this sequence of token embeddings, and this is where you prepend them with your soft prompt embedding or with your custom tokens, and this is actually what's happening here. So, all right, so another thing I was going to show you here is that during this training process and back propagation, you have 124 million parameters from the original model, but this soft prompt embedding layer has only 7,680 parameters, and that should be because each embedding vector has 768 parameters, I imagine. And I say that because we have 10 special tokens, and so if you divide that by 10, that'll be the number of tokens. The main value proposition of prompt tuning is difference between this and this. You're just tuning this very small embedding layer as opposed to all the model parameters. The final comment I want to make on this is that normally if you add a token, if you introduce a token to your vocabulary, you need to change your model architecture a little bit, because that reflects in your embedding, token embedding, by adding a new row to it, but also at the very output layer of the model, where now you need another output node to capture the probabilities of this new token you created. So that does alter your model by quite a lot. Whereas here, you don't need to worry about either. These special tokens don't need to be predicted. And that's why on the output layer, you don't need to add any more nodes to capture those. And because of the trick that we just went over, you don't even need to worry about making any changes to the token embedding layer. You just create your own site embedding layer. Let's see. I think that's about it. And I showed you that the model does work. So I hope that was useful.